My name is Michael Visd. I manage the Centers of Excellence Laboratories for Thermo Fisher Scientific. My presentation this morning is entitled Fast, Accurate, and Direct Carbohydrate Analysis using HPAE-PAD. So as we begin, here's the agenda for today's presentation. On our outline, what are carbohydrates? We'll talk a little bit about their structures. Secondly, we'll talk about high-performance anion exchange chromatography with pulsed amperometric detection. Then we'll go into some application examples. I'll show you some examples using classical separation techniques, and then I'll show you some fast separations using some of the new technology that we have available. And then finally, we'll go in through the total solution that we have available from Thermo Fisher Scientific. First off, we'll start with classification of carbohydrates. As everyone is familiar with, the monosaccharide that we analyze for, monosaccharides typically are sugars that have either 3, 4, 5, or 6 carbons. If the carbonyl group is at the end of the chain, typically that's called an aldose. If the carbonyl group is at any other position, then that monosaccharide is classified as a ketose. And here we have a diagram of the aldoses and ketoses. And so those are the monosaccharides that we're able to analyze for. Next, we'll go into disaccharides. Disaccharide units are typically 2 monosaccharides together with, put together with a glycosidic bond. And so in this demonstration, we're showing that 2 glucoses form maltose. Our last classification are the oligos or polysaccharides. Oligosaccharides typically are a chain of sugars, 3 to 10 molecules in length, where a polysaccharide can be a short chain or a long chain, but typically a linear structure, usually of 10 or more sugar molecules put together through a glycosidic bond. We can chop these glycosidic bonds and then analyze a larger sugar for its monosaccharide components, either through acid digestion or through enzyme digestion. Now, some of the challenges that we've had with carbohydrate analysis in the past is just because they are extremely polar and only partly ionic. Carbohydrates are many similar structures, but those structures are very complex. Carbohydrates are non-chromophoric, and they're often present in very complex matrices such as glycoproteins or glycolipids. Next, we'll look at the technique called high-performance anion exchange chromatography with pulsed amperometric detection. This technique was developed through our column technology from the Sunnyvale R&D group, along with the detector technology that was developed by Iowa State University, all in the mid-'80s. Our column technology allows us to separate neutral and charged sugars without derivatization. That's very important because other techniques require a long, drawn-out derivatization process. We can separate these sugars on the basis of charge, size, composition, and we can even separate things based on their branching or their linkage isomerism. Next, let's talk about pulsed amperometric detection. It's a simple, direct method. Again, no sample derivatization, so all you really need to do is dilute your sample in DI water and inject the sample. Very easy. Very high sensitivity, comparable to fluorescence detection. Minimal sample preparation. Really, again, as I said, we can just dilute our samples by a factor of 100 or even a factor of 1,000 and still have very good sensitivity with this detector. And then some of the other points there, most of our methods that we've developed over the years are now official methods in the AOAC or other groups. Detection is linear over 4 orders of magnitude. And since PAD is a non-destructive technique, now we're able to either take a fraction of the sample as it comes through our detector and now use it in some other instrumentation, say run it into a mass spec. Next, we'll see how these samples are able to be separated. We all know that carbohydrates are weak acids, but at high pH, we're able to at least partially ionize these carbohydrates, which makes them amenable to separation by anion exchange chromatography. You see the chart on the left, and it's showing the relative pKa's of all of those sugar moieties. You'll notice that the higher pKa's are the sugar alcohols, and the lower pKa's are the larger sugars. As they get bigger, the pKa's are smaller. And so we can then basically predict where these analytes of interest will elute off the chromatogram. Here's an illustration of the column technology that was developed at Dionex. And so that column technology has stayed the same over many years, but it's basically a polystyrene divinylbenzene core. Then we surface sulfonate that resin bead, and then we attach our ion exchange sites to that. Those are quaternary amine sites, and those are part of the latex particle that goes on the outside of that bead. And so these latex microbeads then are really the anion exchange functionalities, and so they're the ones that do all the work. Here's a chart that kind of talks about the columns that we have available. I have some of the fast columns circled there. They're the newer columns that we have available. The CarboPac PA20 column, which is very good at fast separation of sialic acids. The CarboPac SA10 and the CarboPac SA10 4-micron column. Both of those columns are good for mono and disaccharide separations, especially in biofuels, foods, and beverages. And then we have our standard CarboPac PA20 column, which gives us high-resolution separations of mono and disaccharides and optimum resolution in larger sugars. Again, there are a few other columns that we have available. The CarboPac PA200 for oligosaccharide separations. The CarboPac PA1, which is the standard column used in many standardized methods. And the CarboPac MA1, which is our high-capacity anion exchanger for doing sugar alcohols. Next, let's look at the detection technique. Amperometry is a technique whereby we measure the current or the charge resulting from the oxidation or reduction of the analyte on the specific electrode surface. When analyzing carbohydrates, we use a gold electrode, and so during the oxidation reaction, electrons go from the analyte to the electrode. In a reduction reaction, now the analytes or the electrons go from the electrode back to the analyte. For basically every separation that we do, the detection scheme is an oxidation reaction, and so then we are measuring the current based on the oxidation of the carbohydrates on the surface of the gold electrode. Now let's go into some application examples, and the first ones I want to show you are classical separation techniques that we've used for many years running carbohydrate analysis. And here we're using sodium hydroxide that we make up from 50% solution. And in this first example, this is the classical separation of the monosaccharides. We call this the mix of 6, with 2 amino sugars in the group as well. And this separation is a very short separation, only about 10 minutes or so, running an isocratic eluent of 18 millimolar sodium hydroxide. Here's an example running the CarboPac PA20 column. The CarboPac PA20 column uses a smaller particle size as well as a smaller diameter column, and so we're able to achieve faster separations and also better resolution than was available previously to this. This side shows a gradient separation of the maltodextrins. Maltodextrins are glucose oligomers, and so going from left to right on those chromatograms, we can see that the first peak is glucose, next peak is maltose, and we just keep adding glucoses as we go on. That top chromatogram actually shows out to DP 50 or so, and so we are actually looking at a chain of glucose molecules that are 50 glucose molecules long. Pretty simple separation. It just uses a sodium hydroxide, sodium acetate gradient, and this was done on the CarboPac PA10 column. Down below is another type of maltodextrin, and maltodextrins are used for many things. Most of the time they are just basically stabilizers or additions to pharmaceuticals as excipients. This next slide shows the difference between the older PA100 column with a larger particle size versus the new PA200 with a much smaller particle size. And you see the improved resolution and sensitivity that are available using the new CarboPac PA200 column. As we move more into biochemistry, now we look at the sialic acid analysis. Bovine Fetuin is a glycoprotein that is very well characterized in the literature. And as such, we have many applications showing the glycoproteins and oligosaccharides from bovine Fetuin. Here we're just looking at the sialic acid analysis, and so we see NANA, which stands for N-acetyl neurominic acid, and NGNA, which is N-glycolyl neurominic acid. Sialic acids are both terminal sugars in oligosaccharides, and so they signal that that is the end of the sugar complex of the glycoprotein. Here again is an illustration comparing the PA100 to the PA200, and notice where I have arrows there on the two chromatograms. On the PA100, well, we can see that there's definitely some material there, but it's not very well resolved. Whereas on the PA200, now I'm getting very distinct and sharp peaks. And so the resolution is much improved, and that's really because of the smaller particle size that we have on the PA200. Now let's get into some new technology where we're able to utilize this new technology to give us even faster separations. And of course, we then develop columns that can use this new technology to do those fast separations. This diagram illustrates where the eluent generator fits into a carbohydrate analysis system. Pretty much the same as where the eluent generator works in our standard conductivity detection. But here, after the eluent generator and after the CRTC, which is the continuously regenerated trap column to remove anionic contaminants, we do our separation and then right to the electrochemical detector. Our first separation uses one of these new columns. This is the SA10. SA10 was developed to do a fast separation for biofuels and foods and beverages. And so here we're using a very low concentration of hydroxide, 1 millimolar only. And this separation is done in about 10 minutes or so. Next separation shows a new method for coffee sugars. Coffee that comes into the plant has to be tested before it's sent out, and so consequently this analysis needs to be done with every batch of coffee that comes out of the production plant. So here we're showing about a 7-minute run or so on the CarboPac SA10 for the sugars that are in coffee. This next slide though is the old method, and you'll notice that this method takes about 40 minutes for the same sugars, and this was done using a sodium hydroxide water gradient. And so basically over time we would decrease the concentration of hydroxide to get the separation to occur. And so you see, compared to the newer separation, it's much, much longer. This next slide shows a PA20 separation. Now this is a capillary format column. So what we've done is developed a column that is only 0.4 millimeters diameter instead of the normal 2 millimeter or 4 millimeter column. And so now we run at very low flow rates. Here we're showing a flow rate of 8 microliters per minute on the capillary system. And so this separation, pretty standard on a PA20 column. It is the same packing as the 2 millimeter and 4 millimeter columns, and so there's really no difference in the separation itself. And as you see, it's about an 11 or 12 minute run, and we're able to elute off the mix of 6 here, which is fucose, the 2 amino sugars, galactosamine and glucosamine, as well as 3 monosaccharides, galactose, glucose, and mannose. Here's a chromatogram using the SA10 again in the normal format now. This is a 4 millimeter format column, but it is a 4 micron particle size column. And so the SA10 first came out in its normal size, and now we've developed a 4 micron particle size, which, as I've said earlier, makes the separation faster and gives us better resolution. And so in this separation, we're looking at lactose and lactulose, 2 sugars that are in unpasteurized milk. Separation isn't so difficult. Really, in this application, it's the sample prep. And as you notice under the sample prep documentation there, it does include a digestion, then a centrifugation, then filtration, and then we can do a dilution and then run the sample on the chromatograph. An example of a biofuel application, here we're doing corn stover hydrolysate. And in this particular application, we want to make the detector less sensitive. And so if you notice there on the gasket, we use a 15 mil thick gasket, where typically we only use a 1 mil gasket. What this thicker gasket does is it slows the linear velocity through the cell. And so consequently then the detector itself is less sensitive. And so because there's an awful lot of sugar here, we don't want to make a big giant-sized dilution. We want to be able to just go ahead and do a small dilution and then inject the sample as is. And that 15 mil gasket allows us to do that. Another chromatogram, this one shows native sugars in apple cider. And if you notice at the bottom, even on the last slide, there was an application note that was referenced there. This one references Tech Note 135. And you could find any of these technical notes or application notes on the Thermo Fisher thermoscientific.com website. Going back to this chromatogram, this is another capillary separation where we're running at 8 microliters per minute. And again, we're looking at the native sugars here, galactose, glucose, mannose, sucrose, and fructose, all in apple cider. Here's an example of a biological application. Here we're looking for the carbohydrates in urine. And so this separation is done with a hydroxide gradient using the eluent generator module. Again, since it's capillary, we're running at about 8 microliters per minute. This separation shows a change in the baseline, which is really due to the change in the hydroxide concentration that we see going from 10 millimolar up to 35 millimolar KOH. And so even with that shift in baseline, we're still able to resolve all of those peaks of interest and still get good detection from all of them. This separation that I'm showing now is a separation using the new PA20 fast sialic acid column. Notice that it is only a 30 millimeter column in length, and so this separation will be done very quickly. Notice that we're also using a sodium acetate, sodium hydroxide gradient here, and so we aren't using the eluent generator module. But this separation, again, does N-acetyl neuraminic acid as well as N-glycolyl neuraminic acid and separates them by about a minute and a half or so. Total runtime, though, of only 3 minutes, and so much better than our 10-minute run that I showed earlier in the slide deck. Another glycoprotein analysis here. The sialic acid, as I mentioned earlier, was those terminal sugars. Here we're looking at the breakdown of a glycoprotein, or we're looking at the carbohydrate moiety off of the glycoprotein where we've digested the sample. And here, again, we're referencing Tech Note 40. And so take a look at that one when you have a chance online. But again, this one uses the PA20 column using eluent generation. But because we are using a low concentration of hydroxide, we want to make sure that that column is clean. And so we do a column regeneration. And you'll notice in the gradient or the eluent profile that we do run up to 100 millimolar KOH for a short amount of time just to regenerate and clean the column. Another glycoprotein sample here. This is monosaccharides in a digested glycoprotein sample. And you'll notice here that we're either digesting with hydrochloric acid or digesting with trifluoroacetic acid. Both digestions give us the 4 sugars that we're interested in: galactosamine, glucosamine, galactose, and mannose. And then you'll notice toward the end we have some other peaks eluting. These are the larger sugars, but since we're not interested in them, they just come off in the wash. And again, this wash cycle is basically used to make sure that our retention time stays stable over the long term. And so going forward, here are the systems that we have available from Thermo Fisher Scientific. On the left is the ICS 4000 dedicated capillary system. And so any of the capillary applications that I've shown you here on the slide deck can be run on this ICS 4000, or they can be run on the ICS 5000 Plus. ICS 5000 Plus can run at higher pressures, just like the ICS 4000, and it has the capabilities of running capillary, 2 millimeter or 4 millimeter formatted columns. The capillary system is dedicated, and so it only handles the capillary columns. And so for conclusions then, I've shown that HPAE-PAD is a fast carbohydrate analysis method, and that HPAE-PAD is one system for monosaccharides, sialic acids, other sugar acids, all the way down the line. If you have any kind of need for a carbohydrate analysis system, then HPAE-PAD is the technique that you should be using. And with innovations such as high pressure ion chromatography and CarboPac columns, carbohydrates can be analyzed in as little as 5 minutes. And so I thank you very much for attending today, and we'll talk to you soon. Thank you.